All things tech, all in one place. Tech Talks.
Okay, let's just jump right in, because what we're talking about today, it's not just an update, it's a breakthrough that could literally change the internet forever. See, researchers over at the University of Pennsylvania, they've just pulled off something that most people thought was, maybe decades away. They sent quantum information using the exact same fiber optic cables we all use for Netflix and everything else. Yeah, this is a huge deal.
But hang on, before we get into the nitty-gritty of how they did it, let's talk about why this matters so much. I mean, what if our internet was just unbreakable, totally unhackable? Imagine a network so powerful it could connect quantum computers all over the world, creating this single, massive machine that could tackle problems we can't even wrap our heads around right now. We're talking about discovering new medicines, new materials, at lightning speed. And look, this isn't some sci-fi movie plot. This is the very real promise of the quantum internet.
So yeah, the future internet is arriving. And the crazy part? It's not just the dream on a whiteboard anymore. This experiment literally took the quantum internet out of the perfect clean lab and plugged it right into the messy real world, using the exact same cables we're all using right now.
And the potential here, it's just staggering. Think about it, unbreakable security. I mean, a system where just trying to eavesdrop on a message instantly destroys it. Poof, gone. We're also talking about supercharging AI, making scientific discoveries that are just impossible with today's best supercomputers. So yeah, the stakes for getting this right, they're about as high as they get.
So what's the magic trick behind all this? Well, it all comes down to this wild idea called quantum entanglement. Now, it sounds super complicated, I know, but here's a simple way to think about it. Imagine you have two particles that are linked, like cosmic twins. If you look at one and see it spinning up, you know at that exact same instant that its twin, even if it's on the other side of the galaxy, is spinning down. It's this instant, spooky connection. That's the secret sauce for quantum communication.
Quick pause. If you like what you see, hit like and subscribe. Thanks for the support.
Okay, so if this stuff is so amazing, you're probably asking, why don't we have it already? Right? Well, that brings us right to the big, fragile quantum challenge. This is the massive wall that scientists have been banging their heads against for years.
And this slide just lays it out perfectly. Our normal, classical internet, it works by looking at your data. A router has to read the address on a packet of data to know where to send it. Simple. But a quantum network? Whoa, whole different ballgame. The very act of looking at the quantum data, it destroys it. It's gone. It's like trying to read an address on a letter, but the second you look at it, the letter bursts into flames. How do you build a network around that?
And Robert Broberg, one of the PhD students on this project, he said it perfectly. You just can't do that in a quantum network. Measuring the particles destroys the state. The old rules simply don't apply. And that, right there, is the fundamental problem they had to solve.
So, how do you solve a problem that seems totally impossible? Well, you get creative, really creative. And that's exactly what the team at Penn did. They came up with this brilliant solution, and they gave it an equally brilliant name, the quantum train.
And the engine of this quantum train, if you will, is this special little piece of hardware they developed. It's called the Q-chip. Think of it as a translator, a bridge between our normal, classical internet and the weird world of quantum information. It's what lets them finally speak the same language.
Okay, so check out how this quantum train idea works. It's so clever. First, the Q-chip sends out a totally normal, classical signal. This is the locomotive. It chugs along the fiber optic cable using all the standard internet rules, TCP/IP, all that stuff, to talk to all the routers and basically clear the tracks. Then, and only then, once the path is clear, the really precious cargo follows behind, the quantum data, tucked away safely in these sealed train cars.
And the lead author, Yiqi Zhang, put it perfectly. The network doesn't need to look inside the train cars. It just looks at the locomotive up front to see where the whole train is headed. That means the quantum info in the back, it stays completely sealed, untouched, and perfectly safe all the way to its destination. It's a beautiful, elegant solution that uses our current internet to protect the future one.
But okay, that's the theory. Getting it to work on a whiteboard is one thing. The real test? Taking it out of the quiet, sterile lab and putting it on a real, live commercial network. And that's what they did. They used Verizon's actual fiber network on campus. And let me tell you, the real world is a very, very noisy place.
I mean, think about it. Out in the wild, those fiber cables are dealing with everything. The temperature changing with the weather, vibrations from construction down the street, even just a big truck rumbling by.
Any of those tiny little shakes could be enough to just completely scramble that super fragile quantum signal. It could derail the whole train.
So, how do you keep the train on the tracks when the world is constantly shaking them? Well, this is where that hybrid idea gets even more genius. They built a smart error correction system that, you guessed it, never has to look at the quantum data.
Here's the logic, and it's awesome. Professor Liang Feng explains that since the classical locomotive and the quantum train cars are on the exact same track, any little bump or jiggle that hits the locomotive also hits the quantum cars in the exact same way. So by measuring the noise on the signal they can look at, the locomotive, they can figure out exactly how to correct for it on the signal they can't look at. It's like seeing a pothole ahead and fixing the train's suspension just before it hits.
And did it work? Oh yeah, it worked. The result was a staggering 97% accuracy. 97% on a messy, real-world network. That number is everything. It proves this isn't just some delicate lab experiment. It's a system that's tough enough to handle the chaos of the real internet. It actually truly works.
So, where does this leave us? What does this all mean? Are we really standing at the dawn of a new era?
Now let's keep a level head here. This is a massive, massive step forward. It proves we can use the fiber we already have, it works with the routers we already have, and that Q-chip, it's easy to mass produce. That's all huge. But there's still a big challenge ahead: distance. You can't just boost a quantum signal like you can with a normal one. So going from a citywide network to a global one, that's the next mountain to climb.
But I really want to leave you with this incredible perspective from Robert Brodberg. He says this feels like the early 1990s. You know, back when the first universities were just starting to connect their computers together. Back then, nobody, and I mean nobody, could have predicted YouTube or Uber or any of the things we take for granted. He says the quantum internet has that exact same potential. This breakthrough might just be that first foundational brick for a future that's impossible for us to even imagine right now.
And that's really the big question, isn't it? We're still at the very beginning, with huge hurdles left to clear. But for the very first time, a quantum signal has traveled on the public internet. So you have to ask yourself, are we witnessing the very first message being sent on the next internet?
All things tech, all in one place. Tech Talks.